Hello, everybody, and welcome to Research Methodology Week 6. This week we're talking about quantitative research. What are the types? And we're going to drill down into different types of quantitative methodology and being able to recognize what these are as we're looking at a research study. And also look at validity and use that to help us critique how strong a particular study is. So we're focusing on these as still sort of our background information before we get into looking at levels and critiquing studies in that way. We need to know a little bit more before we get to that point. We have some announcements. I'll let you take a look at those on your own. Now, this is going to be a review for this part of the talk today. We looked at three major ways to classify literature. We looked at the major methodological approach. We looked at research design and research purposes. And today we're hanging out in research design. We're going to look at these aspects and how each of them have their own validity flaws and concerns, and we'll look at how can we take a little closer look at that validity. So first of all, experimental. This is going to be something that's familiar to you. We have experimental, quasi-experimental, and non-experimental designs, right? And we know that our experimental are randomized controlled trials. This is where the participants are randomized into groups, and this is the primary feature of an experimental design, is that people are placed by random chance into these different groups. Another aspect that is often occurring is that the studies are blinded. So they're usually blinded to the participants. The participants don't know if they're in the intervention group or the control group, whether they're getting the intervention or not. Double-blinded, where the researchers also don't know which group people are in, is also preferred. A really important aspect of an experimental design is that you need a representative sample, and this often is much larger than what you might find in a quantitative quasi-experimental design. Okay? So in a representative sample, you want to make sure that you have enough people in your study that you can represent the population at large. So for example, if I were doing a fall prevention study and I wanted to look at people over the age of 60 in the United States, I would need to make sure that I had a broad enough sample that would look at race, geography, male, female, genders, socioeconomic background, ethnicity, basically all the demographics, right? Rural, urban, suburban, all those sorts of things. We would want to take a look at those features and make sure that we were representing the population at large. And we would need a lot of people at a lot of different sites in order to have a true experimental design. We would be doing this to test an intervention. So in this case, probably a fall prevention intervention, like a class or a series of classes that people might come to. So here are some examples of experimental designs. This is actually found in your textbook, Taylor 2024, Chapter 13. So if you want to kind of spend a little more time with these designs, that would be a great place to do it. So in experimental designs, we are looking at least two groups. And this first design shows that we are doing a post-test only. So R means randomized, T means the treatment group, and C means the control group. So at the first point in time, we're just gathering our group. Then we give the treatment group their treatment, whatever that may be, and then we assess. Okay, that's our A. So this could be, say, the COVID vaccine was tested on a whole lot of people. At point one in time, they just collected all those people. Then they gave some people the treatment. They gave other people a placebo. And then they checked to see how many people in each group got COVID. A two-group pre-test, post-test would be in the case of adding at the beginning of that study an assessment. And what you're trying to do at that point in time is make sure the groups are fairly representative and fairly equal between them. There aren't any big standout differences. There shouldn't be a significant difference between group 1 and group 2 at that first point in time, or between the treatment and the control group. So maybe this is my fall prevention group, and I'm looking at my randomized folks. And in the treatment group, I'm hoping to see people who are very similar to people in the control group. Then the treatment people get their intervention, and then we look at them at the second point in time. Did the treatment group fall less than the people who were in the control group. Delayed treatment control group is often used when we want to make sure that we're being ethical and it's not ethical to not give the intervention. So, for example, in the COVID vaccine trials, I actually knew someone who was in the Moderna vaccine trial, and he said that after the study was all over, they then gave him the Moderna vaccine. So it wasn't until that point that he found out that he was in the placebo group, and he received the Moderna vaccine after the study was all over. And there's no testing at that point. They just give those folks the vaccine, make sure they're getting the same treatment as everybody else. So what are some of the threats to validity in an experimental design? The first is artificiality. This means that we are doing something that looks different from the way something might occur in a naturally occurring environment. So we are bringing people into a lab, we're making them wear a contraption, we're testing them in some way. People know they're being watched, and so they're going to react differently than if they were not being watched, okay? We can also get into the situation where we have unrepresentative samples. So maybe we did a bad job of selection and we selected only people in their 60s for our fall prevention study. Or maybe there were dropouts. Maybe all the frail people in our fall prevention study got sick and dropped out. Well, now we don't have a representation of how often people fall if they're in a frail condition. And then multiplicity. Maybe we're looking at too many variables at once. So in our fall prevention study, maybe not only are we looking at our fall prevention, but we're also trying to put the variables in of, are they taking medications, or are they taking vitamins, or we had them do a workbook at home, or we had them do a home assessment and do some environmental modifications. Well, now we don't know which thing made the change. Right? We did a whole bunch of things at once, and we don't know which thing actually improved their lowered their risk of falling. Couple more terms. So when you say intervention fidelity, or when you read that in a study, what that means is that the intervention was delivered just as it was planned. So they followed the protocol. Okay, if they say it's a limitation that there was not intervention fidelity, it means that something happened, that the protocol was not carried out as it was planned. Bleeding means that a participant that was assigned to one group somehow got hold of the intervention from the other group. So maybe this would be, say, someone who was in the Moderna vaccine trial went and got the Pfizer vaccine while they were on the placebo. Well, they had bleeding. They had an intervention that was not intended for the study. So that could cause some skewed results, right? Let's move on to quasi-experimental. So quasi-experimental are groups that are not randomly assigned. Some of the ways that that might occur is that we might have cohort studies. So folks who are all in a class together and moving through a program together are in a cohort. So we could be looking at a group that naturally occurs, or a group that we formed the cohort by bringing together folks who wanted to participate in a fall prevention study or something like that. So these are either naturally occurring groups or groups that we formed that the researcher themselves placed people into groups rather than randomizing them. Okay, it's also used to test an intervention. Sometimes a quasi-experimental study is used to avoid some of the bias that you might get, some of those validity concerns that we talked about in the experimental study. But a quasi-experimental study will have some biases and validity problems of its own, because the groups are going to be unequal in other ways besides just the intervention that we're providing to them. For example, if we are looking at folks who are in one skilled nursing facility versus another skilled nursing facility, they may not have all the same pieces of equipment that both facilities have, or they may not have the same nutrition that the other facility has. So there's going to be unequal things in both groups. All right, so here is a slide that has some designs. Let's talk about a one-group post-test only design. So this is where, let's say we're doing fall prevention in a skilled nursing facility, and we take this group in this skilled nursing facility and we give them the intervention, they receive the intervention, and then we assess them at the end. Well, what are some problems with that? We really don't know what their fall risk was beforehand, right? So that design may not work so well in that particular case. What if we took that same study and we gave them a 2-group post-test only design? So we had skilled nursing facility A versus skilled nursing facility B. And those in skilled nursing facility A got the fall prevention intervention, and those in B only got usual care, whatever that was. They get the same care that they would normally get in the skilled nursing facility. And at the end, we could assess and compare groups. Again, what's the problem with that design? Well, we don't know if the groups were equal or unequal at the beginning. What if we went back to that first group, one skilled nursing facility, and used them as their own control? So we did a pretest. What was their fall risk like before we did the intervention? We give them the intervention, and then we assess them again and we compare them to the pretest. Okay, so now we have a little stronger study because we can see how they did afterwards. What if we did the same thing, nursing home A and nursing home B, but we assessed them at the beginning to see if the groups were equal and assess what their fall risk was? And then we give one group the intervention, the other group the usual care, and then assess them at the end and see again, are they different? And we might be able to show a little stronger correlation between the intervention and whether or not the intervention made a difference in their fall risk based on the fact that we had 2 groups in the study this time. So those are some examples of some quasi-experimental designs. They look a little bit like the experimental, but what's the big difference? That the groups are not randomized. What are some of our threats to validity in a quasi-experimental design? Well, the centers may differ on some points of equity. So again, back to our skilled nursing facility example. One skilled nursing facility may have equipment that the other skilled nursing facility doesn't. Maybe one has longer hallways or more trip hazards. That's going to be a factor when we're looking at fall prevention. Selection bias. So this could be whether or not people choose to be in the study. Because we are not randomly selecting and randomly assigning people to the groups, people are opting in. And either their selection or the researcher's selection could make a difference in how the study turns out. Also, experimenter expectancy. I know I'm not blinded to who's in the study, and so I'm expecting the group that's getting the intervention to get better. And so I might be infusing some of my own excitement into the group, and maybe that has an influence in how well people in that group do. Let's move on to non-experimental. So these are our descriptive studies and include surveys and retrospective studies where we're not introducing any intervention of any type. Okay, so we don't give people the intervention. We're just looking to see what naturally occurred in a specific situation. So some examples of non-experimental studies. We might be looking at an incidence and prevalence. Incidence means how many people had an onset of the condition during a certain amount of time. So an example of this is how many people got COVID during the year of 2020. Prevalence is over, all of history, how many people in the total population have gotten this health condition. So in total, how many people in the United States have gotten COVID by this point in time. So incidence has sort of a certain amount of time. How often does it occur? And prevalence is how many total have gotten it, okay? An example in occupational therapy might be if we do an observational study of women with chronic pain and we're looking at how often they do particular daily activities, or what's the prevalence of their impairment in daily activities as a result of their chronic pain. So those are some things that we can look at with a non-experimental study if we have a data set that we can look at. So maybe it's retrospective, or maybe it's we find women who have chronic pain and we ask them if they will be in our study. So that would, again, be not a randomized selection. It would be a specific selection. We're going out looking for people with this issue to put them in our study. Okay, some other examples would be a cohort design. So this would be similar to the cohort that we talked about before, but this time we are not introducing an intervention. We're just following this group through. So what if we're looking at a group of children from infancy to toddlerhood to look at developmental patterns and we're just seeing what's naturally occurring? We're just reporting on what is, not introducing something to change it. Okay? Cross-sectional design would be, rather than looking longitudinally over time, we're looking at just at one period of time. So I did a study where we looked at what sorts of ethical problems are practitioners encountering in their first 5 years of practice, and we did a survey at one point in time. Okay. Descriptive case studies or case series. So this could be, how did 7 people who went through post-cancer occupational therapy respond to the intervention? So rather than, we didn't provide any new intervention, we just looked, say, retrospectively at these folks in usual care and looked at what happened in the case of that usual care. It was not introducing a new intervention or comparing it to an old intervention. It was just looking at what was already. There are some threats to validity, of course, in non-experimental studies as well. When you do a survey, you always have this chance that there is a non-response bias. People who ought to be included in the study choose not to do so. They just don't respond. So, for example, with the study that I did asking about ethical problems within the first 5 years of practice, that study had the unfortunate timing of coming out in April of 2020, right when COVID hit, and people were kind of busy with other things. So people who probably should have been responding to that study didn't respond because they were busy. We also probably had a response bias. People in the study maybe didn't recall things correctly, did not interpret the questions correctly, or they were so stressed out by COVID that they were responding in certain ways, or they didn't have the options. Maybe I didn't write into my study the options that would have made the most sense to express their opinions or experiences with ethical issues during COVID. All right, so we've talked about experimental, quasi-experimental, and non-experimental studies, and some of the threats to validity that come with those particular designs, with those research designs. Let's talk about validity in general a little bit more. What are some of the types of validity that we look at? So we have 4 types. And validity, of course, the definition of that from Taylor, and this is actually from the 2017 version because I really like how they worded this. Validity gives us the best evidence available to be able to approximate the truthfulness of a proposition or an inference about the cause. Okay, so did this study, was it valid in providing the best proposition or inference about what's going on? Should the intervention be used? Is it a good intervention to use? We have 4 types of validity that we're going to talk about, and we're going to drill down into each of those a little bit more. Statistical conclusion validity, internal validity, construct validity, and external validity. So with statistical conclusion validity, our definition is that it defines the extent to which an independent variable and dependent variable are related, or that they vary in relation to each other. 3 things come up with this. This is with our statistics, okay? So statistical conclusion means how did our numbers turn out, right? 3 aspects. First, statistical power. Did we get enough people in the study to adequately power the statistical tests? So in order to be able to crunch the numbers, you've got to have a large number of people. There are tests for that. We're actually going to learn how to do that next semester, but right now what you need to know is that statistical power is a thing. Is the study adequately powered means do we have enough data points, which often means did we have enough people to create those data points, right? Statistical significance. This is that p-value that you probably learned about in your undergraduate statistical class. Mathematically, is the relationship likely to not occur by chance? So p-value means the percent value, and we usually want it to be 0.05 or less, meaning we want a 5% or less chance that these results could have occurred by chance. So we want a 95% chance that the thing that we did, the intervention that we provided, actually caused the outcome, not random chance. So a p-value would say if we have a 5% or less p-value, tiny number, then we're saying that it's only a very small percent of a chance that this study, the outcome of this study, happened just by chance, by random chance. That's statistical significance. Statistical power, statistical significance, and effect size. Now, effect size is a statistical calculation that says how important is this difference. And this is super important when it comes to clinical studies, because we may have, say, a 1 pound difference in grip strength from the beginning to the end of our study. But is a 1 pound difference in grip strength enough to make a functional difference? Will people do better at grabbing a jar of pickles if they have a 1 pound grip strength difference? And the answer is no. But if we have a 20 pound difference, well, yeah, that's a pretty big magnitude. So it's the magnitude, how important is this difference? And we have statistical calculations for that. We don't just look at it and go, meh, it looks pretty good. It was 4 pounds. It's all right. The effect size tells us whether or not it was an important difference. So it's the mathematical standardized way of reporting the degree of difference. Okay, it tells us a support for a treatment that goes beyond just whether or not it was statistically significant. It's saying how important was it. We have a couple more terms that are often used in the clinic when it comes to especially our assessment tools. Okay, so effect sizes in terms of any intervention. These next two that I'm going to talk about are specifically in terms of the assessment tools that we're using. And I'm going to use grip strength as our example. So minimal detectable change, or MDC, is a statistical estimate of the smallest amount of change that can be detected by a measure that corresponds to a noticeable change in ability. Okay, so for example, in grip strength testing, how sensitive is a dynamometer? Is it sensitive to within a pound? A half a pound, a quarter pound? How do I know what that minimal detectable change is that is going to show a noticeable change in ability? So we have math for that. The mathematical statistics are going to help us to know that. So we might say with a JMAR dynamometer, the minimal detectable change would be, and it's probably honestly something like 4 pounds. That basically tells us our measurement error. So how much of an error are we going to allow on either side of that 4 pounds before we say, okay, this person actually is showing enough of a change in practice that I can say this is probably making a functional difference in their life. Okay? Actually, that kind of bleeds us into minimally clinically important difference. But basically, the minimal detectable change is just saying what's that smallest amount of change that this instrument can assess for us. Okay? Accounting for errors in measurement. Minimally clinically important difference. Now, this is taking us to the smallest amount of change considered important by the patient or the clinician or others. And again, it's that jar of pickles. Maybe the person shows a 4 pound difference, but are they able to hold a cup of coffee without dropping it? Are they able to open that jar of pickles? Are they noticing changes in their daily life as a result of the change in the number of their grip strength? So that's an important number for us to know as well about our assessment tools. That's a really handy thing to be able to report. If you can say, hey, my person showed a 6 pound change in grip, and they're also saying they noticed these changes in their life. And the data says that if you have 4 pounds or above, it's going to show that there's a functional change. Really useful when it comes to validating your own results in the clinic, using those statistical measures for that. Okay, a little bit more about these things. MCD, the smallest amount of change that the JMAR dynamometer can accurately measure. Is it 1 pound or a quarter pound, or so forth? And the minimal clinically important difference is how much change in grip strength does it take before I can open the jar of pickles. And then taking us back to effect size. If I do this intervention, this grip intervention for 12 weeks, am I going to see enough of a magnitude that I am seeing a clinical difference? All right. So the first two, clinical difference, does the tool show us that? Am I using the right tool? And the effect size in this particular study, using this tool to measure this, did they accomplish that? Okay, lots of threats to statistical conclusion validity. And these all have to do with the numbers, okay? Not having enough power, not using my statistics in the appropriate way. Maybe I used the wrong tool, the wrong Maybe I shouldn't be doing a t-test. Maybe I should be doing a different kind of statistical test. I have to know the right test to use. Fishing for findings or data mining, not using reliable tools. Maybe I didn't use the proper dynamometer. Maybe I didn't carry out my intervention the way that I should. Or maybe if I'm doing a quasi-experimental, maybe there's variations in the settings or in my groups of participants. Okay. Internal validity. So we talked about statistical conclusion validity. Now we're moving on to internal validity. This is the extent to which we may infer that an explanation for a particular phenomenon is true, or that a specific action or intervention has caused the effect. So is the relationship between my independent and dependent variable a causal or at least a correlational relationship? Or did something else cause the outcome? What were some of those confounding variables over time? Did I have a selection bias that made it not appropriate to do the statistical test that I was doing? Did I have internal validity in my study that I did? Some of the threats to internal validity can be history, maturation. So basically, did someone grow? Were we looking at a child and things change? So of course their grip strength is going to change. Did they improve just because they practiced on the assessment tool, not on the intervention itself? Regression to the mean. This one is a little bit hard to explain. I'll do my best. Okay, so if I had 100 people take a true-false test and just randomly fill in the answers, a certain subset of those 100 people are going to score 90% and above just at random. If I took those same people that scored above 90% and had them repeat the test, they're going to be closer to 50%. They might get below 50%. They might get above 50% because they're responding at random. They're not responding because they know the answers. They're just checking true, false down the way. They're going to regress toward the mean. So it's just a statistical phenomenon that those who score really well, if you repeat it, they're going to actually regress to the mean. If people are responding at random and not because there's an actual improvement, they're going to regress toward the mean. So if we see that in our numbers, and we would look at that through our statistical analysis, that's going to threaten our internal validity. It wasn't our intervention that made them better, it was just a response at random. Again, selection bias, it could be because I chose people that I thought would do well. Attrition, all the sick people left. Measurement approach, maybe I did my measurements wrong. Maybe contamination effects, which is the same thing as bleeding. Did we have people get the intervention who weren't supposed to get the intervention? Social threats, that's, environmental, like say, COVID happened and everything changed and that along with like historical events, that kind of goes with that history. If I think back to like 9/11, probably studies that people did during that year of 2001 looked a little different than things that happened before or after because there were social and historical differences to that particular time period that changed the outcome of the study. And then ethical confounds. So if you have something that's unethical in your study, that's going to obviously impact your validity. These are defined a little further in Table 13.1 on page 169 in the Taylor book. We need to talk about errors now. So these aren't threats. These are like the outcome of those threats, what you can have, what happens as a result of those threats. You can have a type 1 error, where this is where you report a relationship when there really is no relationship. It happened by accident. So remember, we have a 5% chance of the statistical significance happening by chance. So you can have a type 1 error when there's really no relationship at all. Often that happens when you have too many variables. You're looking at too many things, and just by random, one of them happens to hit within the statistically significant. Okay. Type 2 error, where you fail to find and report a relationship when one really exists. So it says it's not statistically significant when actually it should be. That often happens because our study doesn't have enough people in it. It's underpowered. We don't have a large enough sample to show that our intervention made a difference. Type 1 error, type 2 error. Very important for us to know. Okay, statistical conclusion validity, internal validity, construct validity. Construct validity says whether or not we may make a generalization about a particular concept or phenomenon based on what I'm observing. Okay? An easier way to say it, are we measuring what we think we're measuring? Oftentimes this has to do with our assessment tools that we're using. Did I use the right assessment tool? So in my doctoral study, I used something called, it was a falls prevention study. That's why I end up using that one as an example a lot. It was an assessment tool, questionnaire, that turned out to be not very valid on the sample that I was using in the time frame that I was using it. I was doing it with like a two session intervention. Wasn't enough to see a difference. It really was not a good tool for what I was using. So in that case, I didn't know whether the intervention or the construct was causing the outcome of my study or was something else. Were there environmental factors that were causing the outcome to my study? So confounding variables, what else was going on? Remember the study that I talked about where I was doing a non-experimental survey and COVID came out at the same time as I was putting out my survey? That was a confounding variable. Expectancy effects, that's where I might insert some of my own bias into the study by getting really excited. Or maybe people have test anxiety and that's going to change their outcome of the study. And then interaction effects, which is, again, another way of saying that bleeding effect, or like there's more factors going on than just the thing that I'm trying to test, and that might threaten the validity of my study as well. Okay, so now we're on to our very last type. We had statistical conclusion, internal validity, construct validity, and external validity. So this is the extent to which we can generalize the inference to other times, settings, places. Can we reproduce it? Can we generalize it to a different setting? Okay. Study conditions can threaten our internal validity, or our external validity. So again, let's say I'm doing a study in skilled nursing facilities for fall prevention, and these are very privileged skilled nursing facilities. They have a lot of equipment. They look really great. Can I generalize my findings to maybe a not as well equipped skilled nursing facility? What about participant conditions? Let's say I did my fall prevention study on all people in their 60s. Can I generalize that to people in their 90s? Probably not. What about environmental conditions? What if I were doing a fall prevention study at the height of COVID versus if I were doing it right now, post-COVID? Would we see some different results based on just the environmental changes or the historical time period that we're in? Okay, we are not going to go into this right now, but I have actually several studies where you can take a look at it and see if you can figure out not just experimental, quasi-experimental, or non-experimental, but what was the design? How did they organize it? Was it a cohort study? Was it a randomized controlled trial? How did the people formulate their study? How did they design it? So think through that and try to really drill down into what's the methodology that they used. So I have several of these on here. I'm going to let you take your time and take a look at those. And I will say thank you very much for joining me today and have a great rest of your day. Thank you.